Okay, we're going to look at transformations, and we're going to get still looking at our matrices transformations in 2 dimensions and 3 dimensions. And we're going to look at what these actually look like and the different reasons for maybe a zero determinant. So in this case, if you have a 2 by 2 equation, which is a1x plus b1y equals c1 and a2x plus b2y equals c2, then there's a unique solution for x and y may be found using the inverse matrix, and that exists whenever the determinant is not equal to 0. Now, what happens when the determinant is 0? So if the determinant is 0, then we can say that there is no inverse, and really what that means is there's no solution to this equation. So just to correct what I've just said, there's no unique solution. So here, when the inverse of m does not exist, your determinant is equal to 0. Oh, just on that, sorry, another way of saying the determinant is just this thing as well. So that wee triangle symbol also means a determinant, or else you could have your determinant m or determinant m maybe. So any of those things could be referred to as a determinant, so we need to know all of those. Okay, here there are 2 reasons why there may be no solution to these equations. So if you think what these 2 things represent, so this represents a straight line, and this also represents a straight line. So if you actually looked at these straight lines, the first one is 3x minus 2y is equal to 1. And if you divided this by this line here, your second line, by 2, you're going to get 3x minus 2y is equal to minus 0.5. So in actual fact, these are 2 parallel lines. So that's why they would never meet. That's why there's no solution there. You've got your first line, and there you've got your second line. Parallel lines will never meet, i.e. there's going to be no solution, and that's it. Okay, so there's a reason there. It says the reason the lines are parallel and hence fail to intersect. So, and the gradient, if I rearranged either one of these, you'd see the gradient is equal to 3 over 2. Okay, the second reason that why these 2 lines may not meet, again here, if you did a determinant of this thing, so if you did the determinant of 3, minus 2, 6, and minus 4, you did a determinant of that thing, you would get equal to 0. So again, it's a singular thing, has no inverse, but why does that happen? The reason for it in this case is if you take your line 2 and you take your line 2, it is just 2 times equation 1. So if I just, to get from here to here, I just multiply by 2. So this first line, or the second line I should say, is actually just exactly the same as the first line. So they are just the same line, so they have an infinite amount of things. So it's not that there's no solutions. There's your line 1 and also your line 2. They're in the same place. So there's actually an infinite amount of solutions all the way along this line. Okay, how we've got this is parametric form. So all they've done here is they've just said let x equal to t, and that means you have 3t minus 2y is equal to 1. A wee bit of rearranging, you're going to have 3t minus 1 is equal to 2y. Go over here, and that's going to be your y then value. Your y in parametric form is going to be 3t minus 1 all over 2. So that's where they have come from. Right, we're going to look at a special case. Now this special case is that of what's called the homogeneous equations. So what that means, if I pick any 2 things here, I'll just do the same ones I had earlier on. 3x minus 2y is equal to 0, and I'll do 6x minus 4y is equal to 0. Now, there are what's called trivial solutions for this. So you could rewrite that one as 3 minus 2, 6 minus 4 times xy is equal to the 0 vector. So the trivial solution for this one would just be that x is equal to 0 and y is also equal to 0. So when this is weird this time, The only way for this solution here, this matrix equation here, to possess non-trivial solutions, i.e. solutions other than x equals 0, y equals 0, is if your determinant equals 0. So the result is the existence of non-trivial solutions, and that implies that the determinant is equal to 0, or in this case, the determinant equal to 0 implies the existence of non-trivial solutions. That does not mean there will be a unique solution. There will never be a unique solution if the determinant is equal to 0, but there could be an infinite number of solutions. Okay, we've just talked about two dimensions, and when we were looking at in two dimensions, the reason there were no unique solutions where either we had our two equations represented two parallel lines, or they represented the same line basically. So the two equations look slightly different, but they were actually the same line. So in this one, there were no solutions, and this one there were infinite solutions. Okay. It's a wee bit more complicated then when we go on to into three dimensions, when we involve the x, y, and the z. So that means instead of talking about lines in 2D, we're talking about planes in 3D. Now, a plane is just a two-dimensional surface. So, like your desk is a flat plane, the board is a flat plane, a page is a plane. So we have to see if we've got three planes. There are lots of different ways that they can meet. Okay, one where there are definitely not going to be any solutions. So the first one I can think of, if you imagine, there's a very bad example, but there you can imagine there's three planes which are parallel. So three sheets of paper, and there is no single point on those which is going to be on every plane. It's not going to work. So there's going to be no solutions there. Another one that we could have, we'll do a slightly better 3D drawing here. You could have plane 1 and plane 2 are maybe the same plane, and plane 3 is going slicing through it. So here there will be solutions, but the solutions will be, there'll be an infinite number of solutions, and they'll be on that line which goes through the slice through the two planes. Okay, another example I can think of, you may have a plane here, and you have another parallel plane, and then you have your slicing plane going through them. So you have there are no points which are on all three planes, so there's no solution here. And another one where you would have no solutions is, we call this like the prism of the planes here. So that it's an A-shaped or a triangular shaped prism. Quite hard to draw, and there's better diagrams on down. But you can see they're arranged in this sort of formation, so there's going to be no solutions there. Okay, I'll get rid of these middle ones here. One more decent diagram to draw. And the last one where there's infinite solutions is the spine of the book. So your spine of the book, you can imagine your planes are cutting through each other. And this line here, where they cut, that's where there's going to be infinite number of solutions. And that's it. So for all of these situations I've just discussed, your determinant of your matrix, so this matrix here, for example, would be equal to 0. Okay, and we're going to see it all exactly how we get to these situations. So three equations have a unique solution. So there's a unique solution if the determinant is not equal to 0. But if the determinant is equal to 0, then we're in one of those situations that I have just described. Okay, Okay, so just talk through what we just said, done the drawings of, and we'll see these in better detail in a wee minute. So case 1 was no solutions, so the planes have no points in common, so the three ways we can have this. So the three planes are parallel, that's the most straightforward one to see. Number 2 is you've got two parallel planes, and the third plane intersects them. And the next one is you've got three planes form a prism, so we'll not worry about whether way of saying it, that really is just the A-shaped one, so that's why there's no solution. And the infinite number of solutions is when the three planes have a common line, so it's the spine of the book, Next one, and this is a weird one, all three equations represent the same plane. And then the last one is two of the planes are the same with the other one crossing. So again, it's a common line. Okay. Okay, so in this one, this is just going through these again. First one was no solutions. So again, you've got your plane 1, you've got your plane 2, and you've got your plane 3 going between them. So you haven't got any common points at all. The next one, again, you've got your plane 1, you've got your plane 2, and you've got your plane 3, and they're meeting in this triangular prism or this A shape, and again, there are no common points. In these last two examples, you actually have an infinite number of solutions. So in this one, your plane 1, your plane 2, and your plane 3, they're all the same plane. Basically, they just look slightly different from the original equations. They're the same plane, so you have an infinite number of points all around, all inside this plane. And in this one, you've got plane 1 and 2, for example, could be here, and then plane 3 is here. So this line going, when you slice through them, is where you're going to have your infinite number of solutions, and you'll get your solution would be a parametric equation of a line in 3D. And in this one, you've got your plane 1, your plane 2, and your plane 3. And again, it's this line here. If you imagine they're slicing through, so it's like the spine of the book. Quite a common one for it to turn up to be. So the span of the book, again, like the last one, parametric equation for that, for all the points on this line. Okay, an example in this, we've got to solve the equation. You've got your three equations. Your first thing to do is find the determinant. So you find your determinant, and we've done all the working out for this here. So you find your determinant, and your determinant works out to be 0. Do this. Now, more often than not, it is going to be the case that your determinant is equal to 0, but you still have to show it. And determinant equal to 0 implies there is no unique solution. So you now have to figure out which of the situations which we mentioned above is it going to be. Okay, so if you do equation 1 plus equation 2, equation 1, sorry, plus equation 3, you get equation 2. So that means there is an infinite number of solutions. So if you see this, if one equation plus another gives you one of the other equations, you're in that situation where you've got an infinite number of solutions. So you could do this another way, as we'll see, where you just try and solve them, and you'll see that you just cannot solve it. You can't get a unique solution when you do it. But we'll see that about what I mean by that in a minute. Okay, so what you have to do in this case is you just go back to this equation. This is our equation 2, this is what we've just found, and you let your x be equal to t. So if you sub x equal to t into this, that gives you that y is equal to 3t, y is equal to 3t minus 2. Now this is putting us back into equation 1. You then get 2t minus 9t, 2t minus 9t plus 6 is equal to 4z plus 1. So then you get 4z is equal to 17 minus 5. Wee bit of rearranging, you get z is equal to 7 over 4t minus 5 over 4. So we had said our x was equal to t, our y was equal to 3t minus 2, and your z is equal to 7t minus 5 all over 4. Okay, so what you've got here, you've got this with the parameter t being done by using x. So you put x equal to t. You could have put y equal to t, and you would have got different values for your x and for your z. Likewise, you could have put z equal to t, and you would have got different values for your y and your x. Doesn't mean they're wrong, they just look different. So if you're working through this and you saw an answer in the answer book, it does not, and it's different to what you have. They have maybe just used to put the t equal to y, whereas you've maybe put the t equal to x, as I had done in this case. Right, in this example, since one equation is a combination of the other two equations, then the situation is the spine of the book. Or if we look back, we know our solutions are in a straight line. It's a parametric equation where x varies as t, y varies as 3t minus 2, and z varies as 7t minus 5 all over 4. We also need to, when deciding this, we need to look back at the original three equations. So you look back at your original three equations, neither of our two lines are the same. So had we looked at these and say, for example, my first equation was 2x, say for example, it was 2x minus 4y equals 5. My second equation, who cares, but x plus y plus z is equal to 10. And my last equation was 4x minus 8y equals 10. Now, if you looked at these equations, if you look at your equation, let's pull up 3. If you look at your equation 1 and 3, 1 and 3 are actually the same equation, because all I have to do for my equation 1 and my equation 3 is I multiply by 2. So if it had been this case, there's still an infinite number of solutions, but my equation 1 and 3 are the same plane effectively. So that would have been the situation. So it's not just that you get this bit here and you realize that that's an equation of a line. You don't just say, well, then that has to be this thing. That is not the case. You have to look back at the original equations and see what was going on. Okay, similar sort of example. It's a similar result as the previous example, but we've done this in a slightly different way. So again, you've got your equations 1, 2, and 3, and what we want to do is find the determinant of those. And when we find a determinant, surprise, surprise, the determinant is equal to 0, therefore no unique solutions. We still need to find out what is going on. I'm just going to label these 1, 2, and 3 up here. So that was my equation 1, that was my equation 2, and that was my equation 3. Obviously, we'll be coming back to these later on. Right, so we know there's no unique solutions. So you know there's no unique solution, so that means you know there's no solution. But the way we do this is a bit weird. We actually try and go about solving this thing. So 3 equations, 3 unknowns. I'm going to say we want to eliminate x. Now if I was doing this in an exam, I'd abbreviate that to just say elim x. So we do that. So if you do equation 2 minus equation 1, my new improved equation is equation 4. And then I do 2 times my equation 2 minus equation 3, that gets me equation 5. Now, if you have a look at equation 4 and equation 5, equation 4 and 5 are what we say is they are consistent. And if you look at equation 4, it is 14y plus 7z is equal to minus 14, and equation 5 is 14y plus 7z is equal to minus 14. So they are consistent. They are the same basically. So from your equation 4 or your equation 5, they're the same thing. And I've decided to make y the subject here. Could have made z the subject, it wouldn't have been incorrect, and just would have looked different. But I'm going to make y the subject, and I get y is equal to minus 14 minus 7z all over 14, which can be tidied up as y is equal to minus 1 minus z over 2. And then we put that back into the equation 1. A wee bit of rearranging, you get x is equal to 6 plus z over 2. And then we let z equal t. So the solution to your line is your z was equal to t. Your y we worked out to be minus 1 minus z over 2, which is now t over 2. And your x was 6 plus z over 2, which is 6 plus t over 2. So this is again a parametric equation of a line. So that is what we have. Okay, right, now this last bit, so it's just look back at your original thing. My equation 1 can't be multiplied by anything to give my equation 2. Likewise, it can't be multiplied by anything to give my equation 3. And equation 2 can't be multiplied by anything to get equation 3. So my 3 equations my 3 planes are all separate planes. There's no 2 planes which are actually the same. So that means you are not in this situation where you have 1 and 2 and then your third plane going through it. That is not going to happen in this case. So here we have to be in the spine of the book territory. Now, so what we have found, let's go through this again. We have got no unique solutions, and we've also got an infinite number of solutions. That means it was the spine of the book, and we've eliminated it being this one because no 2 planes were the same. So that the only other option is it is this spine of the book. So if your equation 4 and 5 had been inconsistent, then there would be no solution, and the only other way for there to be no solution is to be the prism. So if, for example, there's our equation 4 and 5, equation 4, so say your equation 4 had been 14y plus 7z minus 14, but say your equation 5 had been, we'll just change that to be 20, then we would have been in, we know no solutions, we know no unique solutions, I should say. We say no unique solutions and no solutions. Therefore, it has to be the prism sort of shape, which is done very badly there, but that's it. Okay, but wasn't the case in our example. So in our example, we had 4 and 5 being consistent. That means it must be the spine of the book in this case. Okay, this next bit is just on the homogeneous case. So that's where all your equations are equal to 0. But the homogeneous case in 3 dimensions, exactly the same as we had before. There, if you imagine you've got 3 equations, so any 3 equations at all, we have got, say, we've got 3x plus 4y plus 5z is equal to 0, and you've got 5x minus 6y plus 7z is equal to 0, and then x plus y plus z is equal to 0. One easy solution for that would be x equal to 0, y equal to 0, z equal to 0. But so that is what's called a trivial solution for this equation, for this system of equations. For a non-trivial solution to exist, then your determinant your determinant must equal to 0. Okay, so that's a trivial solution. For a trivial solution equal to 0, so if your determinant equals 0, therefore non-trivial solution. And that's it. Okay. Okay, our last example, it says find the value of k for which the following equations have non-trivial solutions and find the solution in that case. So you've got x plus 2y is equal to 0. That's your equation 1. You've got 3x plus ky minus z is equal to 0. And you've got 2x plus 5y minus 2z is equal to 0. So it says find the value of k for which the thing is to have non-trivial solutions. So non-trivial solutions implies that your determinant is equal to 0. So you just find your determinant, and your determinant works out to be, when you work it out, you get minus 2k plus 5 plus 8 is equal to 0, which works out to be, a wee bit of working out, k is equal to 6.5. Okay, if we just put that in, if we put k equal to 6.5, you've got, this is your equation 1, and we rearrange it, you get x is equal to minus 2y. If you sub that into equation 2, you get minus 6y plus 6.5y minus z is equal to 0. And again, so you've got x is equal to minus 2y, and you've now worked out that z is equal to 0.5y. And then we can just check that in equation 3, and it does work, so we have got that right. Now, if we just let, they've just said, well, y equal to 2z, you could have left it the other way and worked through it, would have been fine. But here, if you just say, let your z equal t, where t can take any value except t equals 0, so t is just a parameter, you could say. So we had our x is equal to minus 4t, your y is equal to 2t, and your z you've just said is equal to t. So therefore, that's what you get as your solution. So this is a parametric equation of a point on the line. So the solutions are a line. So it says where solutions are, and there you've got your parametric form, and that's where t belongs to a set of reals such that t cannot be equal to 0. So because if t is equal to 0, it would be the trivial solution, which we do not want. Okay, folks, you're now ready to do the system of linear equations sheet, and that will be us finished with our matrices topic.